Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to describe for you the concept of angular momentum. So first of all, what I want you to focus on is this object right here, right? And imagine it's moving along this path, right, at some velocity, right, which is v here. And we can calculate a momentum for this object. Its momentum is its mass times velocity. Right? Now, if I pick a point in space, that's right here, right, just a generic point out there, and I imagine an axis that is running basically directly at you in a standard like XYZ coordinate system. Imagine that the axis is in the z direction there. Right? Getting back to this particle, all right, once we've determined a point, we can calculate for this particle what's called its angular momentum. And you calculate an angular momentum by taking the momentum mv and multiplying it by r, where r is this distance that is perpendicular to the linear momentum vector. Right? So the units of angular momentum would be kilogram meter per second times meter, or in other words, kilogram meter squared per second. Right? In the language of vectors, your angular momentum is position crossed with the mv vector. And what that means in this example, if I define a position vector that looks like this, right? This position vector crossed with this mv vector here gives you the angular momentum of the particle. Not important to define it like that in a typical physics class. This will be good enough for most of our applications. So that's what angular momentum is. It's your translational momentum mv multiplied by r, the perpendicular distance. This is very similar to taking a force and turning it into a torque by multiplying by perpendicular distance. All right. Now let's talk about the angular momentum of a rotating object. Now, in this picture, I made this a circular or disc-shaped object, but it can be of any geometry at all. It doesn't matter what the geometry is. And this object can be thought of as the sum of a bunch of little objects or a bunch of little masses, right? And if I pick one of those little masses, and I did so right here, this mass, this little chunk, is moving out of v that I would call v sub I, and it has a distance to the axis of rotation that I'm going to call r sub I here for just a few moments. And then we can therefore calculate the angular momentum of this object about the axis of rotation. And that would equal this, the linear momentum mv times the r. All right, now let's talk about what this I is. So again, you have to imagine this disk as broken up into thousands and thousands and thousands of little pieces. This might be like the first piece, and then this one might be the second piece, and so forth. So the I is just referring to which piece are we talking about. The total angular momentum is equal to the sum of the angular momentums for each of the little pieces. So that's equal to this sum, the sum of all the mvRs over that entire object. Now, remember that the velocity, this velocity, is equal to r times the angular velocity. So when you make that substitution here, okay, we get that the total angular momentum is the sum of all of these. And the angular velocity here doesn't really need to have an I on it because all points on this object have the same angular velocity. So it's pretty easy to just rewrite this as the sum of all the m sub I r sub I squareds times the angular velocity. And we recognize, hopefully, that this is what we call the moment of inertia of the object. So we can actually write the angular momentum of the rotating body as I times the angular velocity. So again, this is directly analogous to, linear momentum is mass times velocity. The rotational equivalent of mass is the moment of inertia, I, and the rotational equivalent of v, right, is what we call the angular velocity. Now let's talk about, what types of things, where would we look at this? So let's talk about translational momentum first. Right, the quantity that changes your translational momentum is impulse. Remember the initial momentum of an object, let's call this like mv1 plus f delta t equals mv2. Or in other words, this quantity, right, force times time, that's your impulse, that's what changes your momentum. And we looked at lots of problems where the net force on a system was zero, which means the net impulse was zero, which means the initial momentum is equal to your final momentum. Well, in a very similar sense, your initial momentum, let's call this I1 omega 1, and it is a vector quantity, plus your rotational impulse. Now, rotational impulse, instead of force times delta t, is torque times delta t. That's equal to your new momentum, I2 omega 2. And again, these are vector quantities. There are a lot of problems or a lot of situations that we're going to look at where the net torque on an object is zero. And let me restate that, not just object, the net torque on a system is zero, because a system can be, a bunch of objects. And that would mean that your initial angular momentum is equal to your final angular momentum. So this was just meant to be an introduction of angular momentum. Hopefully it's done that. I think I'll save the examples for another video. Have a great day.